Good evening, everybody. Welcome to our new classroom.
Yes.
Glad you survived the apocalypse. Alex, you want to make your announcement now?
Sure.
You guys know Alex at this point, our ACS, American Chemical Society president.
Looking at everyone every other week. Yeah. Hey everyone, just real quick, this week is National Chemistry Week. Our chemistry club presidents put together a whole bunch of fun, amazing activities, including speakers, socials, and a couple tours. Today they had a speaker and a tour of the Sense of Pure factory, which is just seeing how chemistry is used with involving implementing flavors and drinks and all that sort of stuff. So great event. And then what?
You make any flavor. The guy gave a great 1.5 or like just 1 hour lecture on food and how chemistry relates to food science.
Yep. So main point being here is we have a couple more events throughout the rest of the week, and especially for the speakers, there's always going to be a free food. So feel free to come by and just learn a little bit about chemistry as we talk about it more. And just at the end of the week, there also is a tour that kind of caught mine to see how chemistry is used industrially. So yeah, no, just some great events, and just I'm going to forward the schedule to John, and he will send it out. But just feel free to come by. Please enjoy some food. Here's someone talking about chemistry for about an hour.
Can you send it to me tonight?
Yeah, I'm sending it right now.
Great.
Yep.
Thanks, Alex.
Thank you.
Thank you.
All right. I want to start by building a list of topics that you guys want to review. These can be specific questions from it can't really be from the unit test. Let's talk about that real quick. Candace died.
I would just like to say thank you so much. I was freaking out at 11 o'clock last night.
How can you not? Yeah. So Candace died yesterday all day, which meant that a lot of you who plan on Monday being the day you do your unit test couldn't do it. So just so that in case you didn't read the email, I extended it until tomorrow night. Not an advantage. I hope you guys know that's not me helping you out. That is me making it as risky as possible. It actually means that I can't open up the review test bank for all unit test questions until Thursday morning. So Thursday morning, I'll set a reminder so that you guys can look through all of the questions you've gotten on your unit test and the questions you never got on your unit test. And you can use that Thursday to review for our exam Thursday night. Unfortunately, it's cutting down how much time you have to review. It also means that I haven't even begun to grade my OChem 1 unit tests, because I would have graded those Monday, but I couldn't access Canvas. And I haven't even thought about grading your unit tests, which in my opinion are actually a little bit more necessary for me to give you feedback than my OChem 1. So I'm going to try and grade what I can of my OChem 2 class. Those of you that have submitted already or will submit tonight, I'll grade those as soon as I can tomorrow, if I can. You got a question?
Oh, you answered it.
Okay. So you guys still have until tomorrow night to finish our Unit 3 test, Part A and Part B. I would still encourage that you do it sooner than later. If you can fit it in, wrap it up. I know, it's just like my whole week. And the testing center flooded, so my Gen Chem classes, I had to deal with a lot of stuff. Woo! You know what? Worst midterms week ever. I'm looking forward to the second half of the semester.
What actually happened in the LAC? Is it the same thing that affected the library?
A water main broke in the LAC or next to the LAC. 280,000 gallons of water filled the gym, soaked into the basement, and flooded the basement of the library as well. So all exams, this happened Friday. So all exams Monday were canceled Friday. Friday they sent a message and said all Monday exams in the Redwood Testing Center have been canceled. And then Monday they sent an email and said all Tuesday exams have been canceled, we'll open again Wednesday. And then yesterday evening, I was in a faculty senate meeting, and the provost said, you know what, they've decided they're not going to open Wednesday like they said, they're just going to leave it closed all week so that they can just fix all of the repairs at once and not let students in while they continue to do construction and like make noise and disturb students testing. So now all exams that were scheduled at the Redwood Testing Center this week have been canceled. And some students in here have accommodated testing. So if you haven't already signed up for your accommodated testing, know that you can't do it at all this week on the Redwood campus. It has to be done this week at some other campus. And if that does not work, because every student, probably hundreds, if not in like the thousands of exams, were going to be held this week at the Redwood Testing Center. Those all are being rescheduled now at the other testing centers. So I'm glad that I give you guys your exams in person so that we can just carry on business as usual. Except for, I wonder how many students are over there trying to get into the LAC that didn't read the email. So at least, I don't know. It's a crazy world. I'm tired. So all that to say, unit test is due tomorrow. I haven't had a chance to grade anything. Usually I would have had them graded already today. Let's build a list of questions, specific or broad, that you want to go over today in preparation for our midterm on Thursday in here.
How important is like knowing the benzene nomenclature, like toluene and stuff like that?
Nomenclature will be on the exam.
Like benzaldehyde, stuff like that?
Yeah. Nomenclature will be on the exams. Is that something you want to review?
Sure.
You're not in your head? There might be nomenclature from OChem 1 as well. Those of you that have used the practice midterm from the summer will have noticed that I think at one time I asked a question like, which of the following can be mixed with methyl grignard to synthesize 4-methyl-2-butanol? So you have to know the structure of 4-methyl-2-butanol just by its name, and then be able to look at structures and see what can be used to synthesize it. So nomenclature of aromatics, yes, or of benzene, but also nomenclature of alkane, alkene, alkyne, alcohols as well.
So on the learning objectives for 1, 2, and 3, I think I counted like something like 70-something different reactions.
Did you?
So I know that we can't, we're not encouraged to memorize.
Oh, how many were duplicates?
Huh?
How many were
I
duplicates?
mean, a lot of it was like
In the
fairly similar.
in the unit 3, you remember that they were separated into previously seen and new to this section?
Right.
Did you count all of those again?
I think so.
Because there were a lot of duplicates in unit 3.
Probably somewhere around like 60.
It could still be 50.
But I know
to
we
60.
can't like memorize, and we shouldn't memorize 60 reactions, but like I just wanted your opinion or your guidance on how to best kind of like organize that while we're studying.
I think I tell all of my students this in OChem 1, and it becomes a lot harder in OChem 2 because it gets to be a lot more reactions, but building a table of reactions is one of the best ways to organize all of the conversions that you see. I want to say that there are some reactions that should be pretty easy to catch on to, like most of the EAS reactions: chlorination, bromination, alkylation, acylation, nitration, sulfonation. They're all very similar. And 2 of them use sulfuric acid as a catalyst. 3 of them use AlCl3 as a catalyst. So I want to say there's many that should become familiar that you don't have to even memorize, but you just have to apply them a lot. But if you're studying, and if you have the time for it, building that table of reactions, saying, I have this starting material with this reagent, this is the functional group that I get. You take the time to build something like that, and it locks it into your head better. Or once you've built it, and then you go and do your homework, or you take the practice exam, and you use it, it starts to lock it in your head a lot better. Familiarity is like a better counterpart to memorization. It's hard to memorize these things, but to become familiar with them is a little bit better. Did that answer your question?
I think so.
It is a daunting
Maybe you
task,
could
huh?
just kind of suggest sat down and tried to put a table, and at least compared to OChem 1, it seems like there could be a lot of columns if you let yourself.
Columns. Yeah, like starting material, reagent, functional group. Those are the only columns I would have. Functional group at the start, reagent, and functional group at the product.
I've noticed that like stereochemistry and regiochemistry is
Yeah,
reactions.
that's true. Regiochemistry to an extent. When we did EAS and NAS, we talked about orthopara-directors and meta-directors, which is a different type of regiochemistry. But it is true that stereochemistry is not as relevant here. You will have stereochemistry on the midterm. Things like chirality is stereochemistry. And it can be as easy as a question like, I think this was on your practice midterm. Which of these alcohols, when reacted with methyl Grignard, or which of these carbonyls, when reacted with methyl Grignard, creates a chiral alcohol? So on one hand, I'm asking you to understand the reaction of a carbonyl with methyl Grignard, but I'm bringing in OChem 1 review to see, do you know when a compound is chiral? And otherwise, you're right. Like you can get into the chirality and the stereochemistry a lot, but most of the reactions in OChem 2 just give you enantiomeric mixtures or diastereomeric because there's another chiral carbon somewhere else. So it just gets really repetitive and really boring. In an advanced organic chemistry class, you'd actually spend a lot more time looking at enantioselected reagents. A reagent that does a similar type of reaction, but is chiral itself. So it only reacts to form one chiral center in your compound. So it's not really a part of our learning objectives. But you're right, stereochemistry it's not a hot topic in OChem 2, not for our class anyways. How about we answer this? Which of these carbonyls, when reacted with methyl Grignard, forms a chiral alcohol? Let's call them A, B, and C. I think Killian said B.
So you would say B because if you react it with A, you're not going to have a tertiary carbon, right?
A would not become a tertiary carbon. Does a chiral center need to be
a fully substituted carbon?
quaternary?
An sp3.
No, if you, methyl Grignard, the organometallic, will make an sp3 carbon out of any of these.
Okay.
All of these.
Oh yeah, because of the hydrogens, right? A would give you 2 hydrogens. Wouldn't it? Give you 1 hydrogen.
There's 1 hydrogen now, and I'm gonna
You'd end up with 2.
I'm gonna add a methyl group.
Okay.
One hydrogen, 1 hydrogen. No methyl, methyl added. What forms here? 2 methyls. What forms here?
You have 2 phenols, so sorry.
2 phenols. With a methyl. So if a quick glance doesn't give it to you, sketch them out. Sketch out what the products are and convince yourself of chirality. It seemed like a lot of people were agreeing with B at first glance. No? But is the answer more clear now? Which of the products is chiral? Russell, would you want to add it? Which one? A. And only A. C has 2 phenyl groups attached to that carbon. 2 identical groups can't be chiral. B has 2 methyl groups added to the carbon. 2 identical groups can't be chiral. But A has phenyl, methyl, hydrogen, and alcohol, 4 distinct groups. So I think what you were thinking was reduction. If I made this from an aldehyde to an alcohol, then I would have 2 hydrogens.
I forgot that.
But instead we did acyl addition.
I forgot that carbon has 4 bonds.
Okay. All right. Someone else had another topic. Russell.
Is it okay if I ask questions from the written word? Or
Yes, absolutely.
Okay, can we do the
First question, second option
Yes.
on Unit 1.
No.
On
the
unit-
alcohols in the process.
Unit 3. Unit 3, question 1,
Second option.
option 2.
Yeah.
Okay. All right, we'll go through it. We'll come back to it. I want to keep building. Roha and then Abram.
Adding on to that, could we do, question 2, second option?
Yeah. Abram?
Yeah. How do you know, so when we're creating like resonance structures with EAS reactions
Mm.
and NAS, how do you know if that double bond will go up into the directing group?
Okay,
Can
good
it
question.
create more of those resonance structures?
So we'll look at the sigma complex
Yeah.
for EAS and NAS, and we'll decide, can this group take the charge or not? Okay,
I feel like that's like
it's
probably
okay.
a simple answer.
It's worth it. That's definitely one of the learning objectives. You guys have to, there will be at least one multiple choice question on that, or like a ranking problem even, and mechanisms, right? Where you have to show those, so it's important to know what to do with that. Thank you.
List what mechanisms we could be tested on.
Okay, yeah. I will say, the learning objective documents listed, I'm never gonna ask you to show a mechanism that I haven't already listed as a mechanism that I wanted you to learn. Not gonna happen, right? No, there were no mechanisms to learn in Unit 3, which is why your written work for Unit 3 was 2 multi-step synthesis problems. There will be a multi-step synthesis to solve on the exam as well. But we talked about grading and how I grade them, which means that you can actually kind of leverage that to figure out how many steps that synthesis can be done in. I really thought hard about the synthesis problems I put on there. I built one, and then I was like, I think this is a little too confusing, so I scrapped it and put in a different one.
So what's the one you put on the exam?
Well, it looks like. What else do we want to put on there, Nira?
I was gonna say if you can give us another example of a multi-step synthesis where we guess the reagents and it's not the structures. I don't know how you use it.
I call that a roadmap. Yeah. So similar to one of the problems you had, I think I gave this to you already, so this is not giving away if you haven't done your unit test. But part B is one roadmap, one multi-step synthesis. So we can look at a roadmap problem. Have you done the practice midterm already? I think I want to leave as many problems on the practice midterm for you guys to practice with. So I'll go back to an older midterm, and we'll look at a midterm there, an older midterm, to do a roadmap problem. Hi guys. Did you come from the LAC? Yep. Sorry. What else?
I was wondering if we could review acidity and basicity when making an alcohol,
Yes.
and then also like throwing in. I think there was a question. I don't know if it's reactivity with like heat versus elimination and substitution.
Oh, okay. So like SNE competition.
Yeah, to form like least substituted alcohols versus most substituted.
Okay, so heat is temperature control. Do I want the reaction to follow substitution, or do I want the reaction to follow elimination? And we can use heat or low temperature to guide that. But then if we're going for more substituted or less substituted, that changes more like the type of base we use. So maybe we just do a quick overview of this, substitution elimination. Although, remember this was like in the OCHEM 1 review reactions, and there were a number of OCHEM 1 review reactions that came back up later in the semester, like radical halogenation, when we talked about aromatics, benzylic reactions, a lot of things with alcohols. And because of that, I do lean into the OCHEM 1 reactions that were present in the other sections a lot more. So it's unlikely that I would ask you a question like, what reagent should be used to give me these two structural isomers? Is that what you're getting at?
Kind of, yeah.
So this is not a question I typically lean into. I would put that on OCHEM 1 for sure. We haven't used alkenes a lot yet, so we're not going to use this. You're not going to see it much. But let's talk about the competition a little bit, and we can do a review of some other things. Competition. Okay. Abram, you had your hand up again?
Yeah, it's kind of something similar. There was a question 16 on the practice exam.
Okay.
It talked about reactivity between certain atoms around the benzene ring, and you had to rank them.
Okay. I'll pull that one up.
And then also like ROH or alcoholic acidity.
Yeah. Okay, good. Oh, you know what? Those were not alkyl halides, though. They were aryl. Is that right?
Yeah, they were.
Okay, we'll come back to that one. We'll pull up the exam.
Installation mechanism?
Acylation?
Yeah.
Definitely.
And alkylation.
Okay. What else?
Can we also do an NAS with alcohol mechanism?
NAS with hydroxide, right?
Yes.
To make a phenol.
Yes.
Good. Because actually, if you have an alcohol on the aromatic ring, you can't do NAS. It inhibits the reactivity. But you can make an alcohol by using hydroxide.
Yes, that's what I meant. Sorry.
Great. Let's do it. What else? Cooper.
So using organometallics to form change into rings.
Okay, yeah. Organometallics into rings. And while we're at it, let's talk about organometallics with epoxides. Because I think we got cut short here last week on that exact topic.
That includes ring closing and opening, when it happens, why it happens, where.
Yeah, well, this would be ring opening. The epoxide ring will open. But I think Cooper's question was ring closing, making a ring by using an organometallic.
Is phenol and phenol the same thing?
Depends on how you're spelling it. Phenyl with a YL is a benzene group. Phenol with an OL is hydroxybenzene.
I'm just gonna review with you. Do we have the Des-Martin reaction overview?
Which is DMP.
Yeah.
No. Did you guys see that on the active?
Yeah.
Gotta take that one off. I'm sorry. Des Martin, if I'm not mistaken,
Makes like an aldehyde.
it behaves as PCC,
Okay.
but you won't see it. You won't see Des Martin as a reagent. Yeah. Just PCC, chromic acid, and MnO2, manganese dioxide, as your selective oxidizer. We can talk about our oxidizers again. We got a full list. What else? All right, let's start diving into these, and we can always come back to them to add more if we have time. All right, when it comes to nomenclature, how many of the mono-substituted names do you remember? Somebody already gave us this one. What was this? Benzaldehyde, which can also be drawn as this, or it can be drawn as this. I hate to say it, but during the Unit 2, Part B, when you guys were giving me mechanisms, one of the questions had a benzaldehyde on it, and a lot of people showed me the last step, deprotonating, taking away the benzylic hydrogen to try and reform aromaticity, because they saw this as the final product, but they had been drawing this throughout their structure. Why are these the same? We can assume hydrogens on carbons to satisfy octets, one of our bond line rules. Okay, so this is, again, one more time. Benzaldehyde. I'm going to abbreviate my aromatic ring now. What about this, which can be drawn a few different ways? One more time. Benzoic acid. Good. All right, all of the other ones have a little bit more of a systematic name. These two, you have to change the suffix of benzene. You have to get benzaldehyde and benzoic acid. Bromobenzene. Chlorobenzene. Now you guys give me some. What are some of the other mono-substituted groups that you knew the names of? Phenol. How else could we call phenol? Hydroxybenzene. All right, raise of hands. Oh, I can't see you though. Give me another one. Aniline. What was on aniline? NH2. What's the systematic name? Aminobenzene. Phenol, hydroxybenzene. By the way, you don't need to be writing these down unless you forgot them. Aniline, aminobenzene. What else? Oxybenzene? I think you're close, but if there's an ether, you need to name the alkyl group too. Methoxybenzene. Anybody remember the common name of methoxybenzene? Anisole. After the man. Oh, I don't know. Maybe. Jamie. Toluene. What comes off of toluene? Methyl. What is the systematic name of toluene? Methylbenzene. Pretty easy, actually. Any other ones?
Is it aniline or
Tomato. But what it's not is alanine. Alanine is an amino acid. Any others? Xylene is one. This was one that I actually didn't give you. But actually, xylene is a di-substituted. Xylene is one we didn't talk about much. That's orthodimethylbenzene, meta-dimethylbenzene, and para-dimethylbenzene. Orthoxylene, metaxylene, paraxylene. What other monosubstituted groups did we have? Nitrobenzene. What comes off of nitrobenzene? NO2. Is there a common name for nitrobenzene? Nice. Not that we discussed. Yeah. Any others?
Is there a sulfonyl one?
Sulfonyl benzene. SO3H. And actually, if you have sulfonyl para to toluene, then you have a tosylate group. And you can hear toluene, tosyl, sulfonyl and toluene, tosylate. You guys remember tosylate as an Oken-1 reagent, TSCl, tosyl chloride. And it helps remove alcohols by making it tosylate. Any others?
Is that reagent going to be used in our?
No, not necessarily. Those are all that I remember as well. So then we start combining them. When am I allowed to use ortho, meta, and para? When there are only two groups, di-substituted benzenes. No more, no less. Regardless of whether you use a systematic name or a common name. So let's draw this compound. Orthomethylphenol. Meta-nitrobenzaldehyde. Para-chloromethylbenzene. Tosylate doesn't have anything to do with thiol. Yeah.
That's a pseudohalide.
When it's connected to a group, so if this was like connected to a carbon chain,
How is that a pseudohalide?
oh, why do we call it a pseudohalide?
Because it acts like one, right?
Because it leaves like a halogen does. Yeah,
That's the only reason.
correct.
Okay.
Yeah, that's the only reason. Not because of its size, not its electronegativity, not its induction, not its polarity, just the fact that the bond breaks in the same way that a halogen breaks. Relative to other CO bonds. Okay, are you ready? What's another way you could name that compound? One hydroxy 2-methylbenzene. Yeah.
Is there wrong if we have them flipped?
Not wrong at all. That compound is achiral, which means that you can rotate, flip in any way that you want to, and it will superimpose. Yep. In fact, it doesn't even need to be on those two positions. Yeah, could have been on any positions.
As long as they're visible.
As long as they're 1-2. Yeah. I'm not sure if vicinal is the right term on
A ring.
a ring, but as long as a benzene ring, but as long as they're ortho, for sure.
Okay.
What other names could I give? Hi there.
Hey, do you have a key for these other rooms on this side?
I don't, just this room.
Do you know who we can call to get someone over here?
Yes, faculty support, which is actually second floor of the TV building as well.
Just over here?
Yeah. What other names could we give this? 1-hydroxy 2-methylbenzene. What else? You wouldn't have to say phen-1-ol, because if you use a common name, it's implied that that group is at position 1. So 2-methylphenol, that works great. What else? There's way more. These are all legal IUPAC names. Why call it phenol? Why not make OH a substituent and make methyl toluene? What could you call it? James? I can see it's on the tip of your tongue. 2-hydroxytoluene or orthohydroxytoluene. Not illegal at all. Jamie, you want to add a little?
I was gonna suspect.
Okay. That's pretty much it, actually. Those are all the ways you can go. All right. M-nitrobenzaldehyde. Once again, Neura, same thing here. You can go on any position for any of these two groups, doesn't matter where, just as long as they are 1-3 related. Could I give any other name for this?
2-nitrobenzaldehyde.
Not 2-nitro.
Oh, 3-nitro.
3-nitrobenzaldehyde. I would not encourage you to name the aldehyde as as a substituent. I would encourage you to always call it benzaldehyde. You can, and it makes it, I think we said it was carboxyaldehyde or carbaldehyde, something strange. It doesn't sound right. So, our last one. What names could we give this other than parachloromethylbenzene?
Or
4-chlorotoluene or parachlorotoluene. Any others? We can't call it 4-methylchloro.
4-chloro.
We can't call it 4-chloromethyl. If you want to use those numbers, we're going to have to name each of them separately. 1-chloro, 4-methylbenzene. Parachlorotoluene is probably the easier one to write because it takes methylbenzene and shortens it to toluene. Common names, systematic names are perfectly legal on the exam. I do my part to stay away from common names when giving you a structure. Remember that benzoic acid and benzaldehyde are not common names, those are systematic. But I try to stay away from anisole or aniline, toluene, but I do want you to be familiar with them. It should be feasible for you to interpret what they are, but I'm not going to require that you like name a compound with that or something. All right. Was that a good review of the nomenclature? Yeah? I guess there's one other version I kind of want you guys to think about. This was on the, no, you know what? I'm not going to do the one there's a similar one that's on the practice midterm, but I want you guys to think about this tri-substituted compound. You guys know this, propofol. There's a lot of different names we could name this. You can't say it because we just talked about this the other day. How could we name this compound? 2,6. No, you're right. 2,6. But how many isopropyls? 2,6 diisopropyl phenol. Or hydroxy comes before I. A, B, C, D, E, F, G, H, I. Nice. They're right there next to each other. So we could call this 1-hydroxy 2,6 diisopropyl benzene. But I think the 2,6 diisopropyl phenol makes the most sense. Why can't I say meta-diisopropyl phenol? Polysubstituted. It's more than disubstituted. Plus, is this meta-diisopropyl phenol, or is this meta-diisopropyl phenol? Or is this meta-diisopropyl phenol? Yeah, they're all meta-diisopropyl, and they're all 3 different structural isomers. So maybe you'd want to say diorthoisopropyl phenol, but we can't say diortho. Okay, good on nomenclature. Any follow-up questions? Anybody mad if I start erasing what I have on the board? Okay. Since we are going to be looking at a lot of reactions coming up, I think I'll talk to you guys about the table of reactions that I would recommend here. Functional group of your starting material, the reagent you're going to add, and the functional group of the product. Actually, there is another column you could add. Here's the other column. You could add notes. Those are just important things that you want to consider. In OChem 1, I talked to my students about having a table of reactions like this, and the notes are things like Markovnikov addition, or anti-addition, or carbocation intermediate, which means carbocation rearrangements are possible. Your notes here might look like this. If you want to say, I have an epoxide starting material, and my reagent is water, then I might have a note that says acidic conditions, more substituted carbon is attacked. And then my functional group here would be a vicinal diol. But epoxide runs a ton of different reactions. So my next step might be, you guys remember what Rn is an abbreviation for? Organometallic. M is our metal. This is basic conditions, which means I'll attack at the less substituted carbon. And if you want to talk about a functional group that forms, you really just make an alcohol, but you also add a carbon-carbon bond. That's one of the characteristics of opening an epoxide ring with an organometallic, is that you create a carbon-carbon bond, and on the adjacent carbon to that, you create an alcohol. I think while we're on this, I want to take a second to talk about ring openings of the epoxides. All my markers. When we open an epoxide ring in acidic conditions, so if I have something like methanol and acid, the first thing that always happens in acidic conditions, something acts as a base. Something becomes protonated. And we showed on our worksheet that that something is the epoxide. The epoxide will get protonated, and the bond to the more substituted carbon will get stretched because that more substituted carbon can hold the positive charge more. So I know that my nucleophile will attack at the more substituted carbon, which is what we said here. So my alcohol forms on the less substituted, and my ether forms on the more substituted. Those are 1, 2. I can map my carbons if you'd like.
Reaction steps, or is it at once, or is it?
No, this is at once.
Okay.
Yep. Because methanol is a weak nucleophile. I can't have methoxide, CH3O minus, in the presence of an acid. It would be protonated, and it would be methanol. So here, my nucleophile attacks at the more substituted position, carbon 2. If I had basic conditions, if I had NaOCH3, I would then need to follow it with acidic conditions. First, NaOCH3, second, H3O+. That might actually be something to say here in my reagents. First, something basic like Rm, organometallic, followed by an aqueous workup in order to get an alcohol out of this. So let's take this same reagent, this same epoxide, and let's add a carbon-carbon bond. Let's use phenolithium in the first step. Basic conditions. Organometallics don't exist in acidic conditions. So this has to be basic conditions, which means that my nucleophile will attack. Here's my nucleophile. It will attack at the less substituted position. It will make an alcohol on the more substituted position. But in this first step, it doesn't make an alcohol. It just breaks a CO bond and it makes O minus. So I have to follow this up with H3O plus. This gets treated with H3O plus, which allows me to acquire my desired functional group, the alcohol. This was something I don't think I clarified well last Tuesday, which is that acidic conditions don't need an aqueous workup. You will have an alcohol. It will be protonated. In fact, the oxygen that becomes the alcohol gets protonated first. So it will open and be an alcohol. Whereas in basic conditions, you'll always make an alkoxide first that needs to be converted, worked up into an alcohol. Those of you that did lab, you did an organometallic reaction where you did acyl addition, and you paused when you made the ionic alkoxide, and then you added acid, and that's how you made the alcohol.
That's what I was going to ask you. So if you have the two steps, so if you have a workup that implies two steps,
Correct.
and then one of the, I guess the intermediate is going to be an ion, so that means it's a salt,
Yep, it's a salt.
which means that we wouldn't have any bonds or arrow pushing because there's no electrons moving. Do we even need to draw that intermediate?
You never have to. No. If you're giving me a multi-step synthesis and you have a step that requires an aqueous workup, I don't consider that aqueous workup an additional step. In the same way that if you're doing hydroboration oxidation, first hydroboration, second oxidation, first BH3, second basic aqueous sodium hydrogen peroxide, NaOH, H2O, H2O2. I consider that one step in a multi-step sequence, despite it actually needing to be done in two portions. Does that make sense? That's one conversion. I don't get what I want until after both of those steps are done. So that's one step.
But in our mind, we'd almost have to say this H, this hydrogen isn't coming from nowhere.
It's not coming from nowhere.
This
It
is
comes from
coming
the
from
aqueous workup. So I actually got a couple of emails after students completed the unit test, and they said, oh, I didn't know that I could do something in acidic conditions. It's not in acidic conditions. It's being followed by acidic conditions. The fact that the 1,2 is there tells you this is acidic conditions. This has to be basic conditions. You don't even have to guess.
Would you and would anyone show it as pH minus?
I don't know anyone that would show that as pH minus. So. Right, Jeremy?
Could you finish the example or show the example in the notes where you have RO minus?
Yeah. Are you saying I didn't complete that?
No, I think you did. You go over that one.
Okay, so similar to this, but if I did this in basic conditions, I'd have to say first NaOCH3 followed by H3O plus. Now I get a different structural isomer. My ether attaches to the less substituted carbon. My alcohol forms on the more substituted carbon.
Methyl is the R.
Methyl is R. Yep.
So if it's in acidic conditions, you'll write the reagent as an alcohol.
That's right. Because alkoxides don't exist in acidic conditions. You can't have an alkoxide and be in a pH over, I mean, not even 7, a pH over like, I'm not sure, I don't have a good number, 5 maybe. So alkoxides don't exist in acidic conditions. If you have an alcohol, then we do consider it acidic conditions. That 1,2, it's important. I'm not just saying I need this and I need this. I'm actually saying first I will mix these together and I will wait for the reaction to come to completion. Then I will mix this with it and I will do a second reaction. an acid-base reaction.
Sorry, I know this is a little punitive. Are
It's okay.
you saying in the notes section that it's the more substituted carbon, but there is more substitution that occurs because of that environment?
Okay, so you have to pick a lane on how you like to discuss it. I like to say that the nucleophile attacks on the more substituted carbon, but some people actually like to say every epoxide will open into an alcohol. Although that's not totally true, because if you stop in basic conditions, you have an alkoxide, and you could use that alkoxide in a Williamson ether synthesis and make an ether. It's the same as any alkoxide. But for the most part, you are opening an epoxide 9 times out of 10 to make an alcohol. So some people would like to say the alcohol will form on the less substituted carbon, what we saw here, or the alcohol will form on the more substituted carbon, what we saw here. I like to think of it as where will my nucleophile attack? Because I look at these reactions as nucleophiles attacking electrophiles. Other people, you may have a different opinion, and you might like to say in the notes, I want to talk about the functional group I will get. I will get the alcohol on the more substituted, or the alcohol on the less substituted. Either is perfectly reasonable. You just have to decide what works better for you. Any other questions on organometallics with epoxide? You guys feel good on that? Let's pull up these questions from the practice homework. I've said this before, I want to say it again. If you have missed a homework or you are not happy with the grade that you have on a homework, turn it in again. Turn it in until you get 100% on your written work. The written work is meant to be mastery based. I want you to master it, so keep turning it in. That goes until the final exam. You can turn in Unit 1 through Unit 5 written work until you come in to take your final exam. Does that seem fair? And why do I ask that? Because the final exam is cumulative. So I want you to have those skills that you've been accumulating all semester. Oh, that is not the file I wanted. Oh, another thing. These written works are not downloading well for some of you. The images, I didn't realize this until recently, but the images that I'm putting in here are actually cropped images. They have like at least 2 other reactions underneath them, and I've just cropped the image to show just one of these reactions. And some of you are downloading these, and the image is uncropping itself and then resizing to this height. So it looks like there are these really tiny sets of 3 reactions. It's not what I'm trying to give you. So if it ever looks like that, it should always look normal on Canvas. So you can just download it and look at the 2 reactions I'm suggesting you do, rather than trying to decipher what those structures look like. I will try to find a resolution to that. I'm sorry for what's been going on, though. All right, so we're looking at this structure. Is that right?
Yes.
All right. What are the 3 tips that I give in multi-step synthesis problem solving? Anybody have one of them? One more time. Map your carbons. Good. That tells you whether you lose some, gain some, and what carbons are doing what chemistry. So map your carbons. What else? Work forward and backwards, which is actually set number 3. What else? Brainstorm. You guys got it. Somebody listened. Work forward and backwards. I know for some of you, the working backwards part actually doesn't come easy. And so that's where I want to start with this problem, is working backwards. But first, let's map our carbons. You guys know the difference between just counting and mapping?
You gotta keep the numbers consistent.
Good. Mapping should go on the starting material and on the product. And you want to keep your numbers consistent so that you can see where the chemistry is happening. So in this problem, what we see is that from the aromatic ring to the benzylic position, I'm adding a 3-carbon group. I mean, I drew it a little bit differently. A 3-carbon group where 2 aromatic ring, benzylic, aromatic ring, benzylic attaches to that 3-carbon group. Let's brainstorm. What reactions might be useful to put in here? When you brainstorm, you want to use your table of reactions. What can I do with this? After I've done that, what are things that might be useful to do? And how can I make this from that table of reactions when you're looking at these are all the ways I've seen how to synthesize alcohols? You're saying, here's a reaction I could do that synthesizes this alcohol. Any brainstorming tips?
Could we use a radical halogenation to start?
So tell me why radical halogenation might be useful here.
Because there's no like double bonds that we can use in both bonds.
Can't do alkene addition. Also, the radical halogenation has regioselectivity. It prefers the most substituted carbon, or it prefers a benzylic carbon. And I want chemistry to happen at my benzylic position. I don't want to do anything with the aromatic ring. I'm not looking to do EAS or NAS because my aromatic ring stays unchanged. What else could we brainstorm? Maybe we could make a Grignard. After we do radical halogenation, we could make a Grignard. Here's one of the reasons a Grignard or organolithium might be useful. I need to make a carbon-carbon bond, and Grignards do that really, really well. So again, radical halogenation because I need some benzylic chemistry. Grignards for a carbon-carbon bond formation.
You just have the Grignard have a carbonyl in that spot, and you just reduce the carbonyl.
Okay, it is actually reduction when you do acyl addition, but we call it acyl addition because we reserve reduction for a different class of reactions. LAH, NABH4, those are reduction reactions.
Yeah.
I want to touch on what you said again. You want me to put a carbonyl here.
No, in the Grignard. Where you want them.
Are we thinking of putting the Grignard here? We make the radical halogenation so that the halogen goes here, and then we're thinking, was your thought to make the Grignard at that position? And you want the carbonyl on carbon 2, or you want the carbonyl on carbon 3?
Could you have an alcohol already on it?
Alcohols and Grignards don't mix. But I do want to touch on what you're saying. You're saying that not just making a Grignard, but using the Grignard for acyl addition. That's what you said. Does anybody want to throw out the idea of acyl addition, or does anybody want to lean into why acyl addition might be good, why it might be useful? You cannot make a double bond with acyl addition. You don't need an alkene with acyl addition.
I'm saying when you use like an organolithium, the R group could have an alkene that you can form the alcohol out of.
That's true. Although that would, I don't know that it would be useful. Well, let's come back to it. Abram, you wanted to add something?
Doesn't that have to be like a ketone or aldehyde?
Acyl addition, for now, acyl addition is reserved for aldehydes and ketones. Acyl addition does not work with carboxylic acids. Why? You cannot have an organometallic in the presence of an acid. They don't exist. It would simply deprotonate the carboxylic acid, and you wouldn't have a Grignard anymore. Let's talk about acyl addition. As a reaction, what functional group does it create? Primary, secondary, and tertiary alcohols. Acyl addition forms a carbon-carbon bond and creates alcohols. I'm putting this as R double bonded to O because the alcohol, ROH, is the R of a carbonyl. So Brett, I think your idea was I could make some organometallic and I could have it be attached to carbon 3, and then I'll have carbon 3 attack carbon 4. That would be my carbon-carbon bond formation. I wouldn't need to do acyl addition.
What am I thinking?
And then I could use the,
What's the other one called?
no, just substitution, I think you're thinking of. Like have an organometallic substitute. Do you guys feel like this makes sense? A Grignard does carbon-carbon bond formation. A Grignard in acylation makes a carbon-carbon bond and makes an alcohol. I want to make an alcohol. What type of alcohol do I want to make? What carbonyl precursor is needed to make a secondary alcohol by acyl addition? Aldehyde. The aldehyde is like a primary carbonyl. So I make another carbon bond, that makes it secondary, and now it's an alcohol. If I wanted to make a primary alcohol, and by the way, these are things that can go in like a table of reactions. Here's the functional group I want to make. Here's the functional group I need to start with. How do I make a primary alcohol by acyl addition with an organometallic? What do I need as a precursor? Primary alcohol has one carbon going to what used to be the carbonyl carbon, and I formed that carbon-carbon bond by acyl addition. So how many carbons was the carbonyl bonded to at the start? One primary alcohol with one bond formation through acyl addition. 1 minus 1, 0. What carbonyl has 0 carbons bonded to it? Methanal. Or I think you can call it methane aldehyde. But most of you know it as formaldehyde. Just a 1 carbon carbonyl precursor. I attack that with an acyl addition with a Grignard, and now I have a primary carbonyl. Then I substitute one of those groups for an R group. I have an aldehyde. I attack that with acyl addition. I get a secondary alcohol. If I substitute both of my hydrogens for R groups, and I attack that with acyl addition, I get a tertiary alcohol. There is no tertiary carbonyl. I can't add another carbon bond that would break the octet. And there is no quaternary alcohol. So these are the 3 precursors to alcohols by acyl addition. And we decided that since we have a secondary alcohol comes from an aldehyde. That's all we need. Those are the only reactions that we really need. So I'm going to recommend that we actually start backwards. So I'm going to show, this is what we'll do to go forward. I'm going to end up having to come to this from that side, I think. I want carbon 2 and carbon 3 to form a bond. Which carbon was the carbonyl? Carbon 2 or carbon 3? It's still bonded to the oxygen. So I have my bicyclic precursor and I have my carbonyl reagent. 3, 4, 5, 1, 2. What do I need to have attached to 2 in order for this acyl addition to work? I need to have that Grignard attached. MgBr. Here's how I would write this over the arrow. I would say first, add this carbonyl. Second, aqueous workup turns the alkoxide intermediate into the alcohol. Now do we see a route to make that Grignard reagent? Radical halogenation. What are my reagents for radical halogenation? Could I use Br2 and FeBr3? Those reagents give me what? Yeah, EAS. That gives me Br2 on the ring, bromination of the ring. Could I use Br2 alone? Yeah, I need a radical initiator. So Br2 and H-nu is what's necessary. Because this is a benzylic reaction, I actually could also use NBS with light. NBS is a compound you guys won't really need to draw ever, but it's called N-bromosuccinimide. And it is also a radical bromine source. It only works at these benzylic positions. Either of these would work just as well. By the way, I don't think I put NBS often on the exams. I put Br2 and H-nu a lot. How do I get to my Grignard from here? Mg. You could put Mg with ether. The ether is similar to what you guys did in lab. It's just to make sure there's nothing protic. There's no methanol, there's no alcohol. There's no alcohol, there's no water to donate a hydrogen. Rusa, what do you think? Any questions remaining on this?
No. Thank you.
You're welcome.
Instead of making the Grignard on the starting reagent, could you make it on the aldehyde or the aldehyde?
So we still need to have a carbon-carbon bond formation, right? Oh, was your question, could I have like this?
Yeah.
No. You cannot. At the very least, I've never seen it.
Okay.
I find it to be unstable because this carbon is both losing electrons to the oxygen and stealing electrons from the magnesium. So I worry that this just wouldn't stay as is. At the very least, organometallics are drawn to carbonyls. So I would worry that maybe one equivalence of this would react with another equivalence of this as well. Yeah. But your idea there was just form the carbon-carbon bond that way and then reduce the ketone to an alcohol. In fact, one of the things we didn't brainstorm about here was reduction. There are other ways to make alcohols. I think Brett had the idea of having an alkene here and doing substitution with the Grignard to make carbon-carbon bond formation, and then using the alkene and doing hydration, putting an alcohol onto the alkene. That's another way to make an alcohol. But the alkene that would have been possible, it doesn't have any good regioselectivity. If I did like oxymercuration reduction, I'd get 2 structural isomers. If I did hydroboration oxidation, 2 structural isomers. If I did acid catalyzed hydration, I would definitely rearrange. The fact that we wanted to both make a carbon-carbon bond and make an alcohol, it rules out reduction. I'm not going to do reduction to make an alcohol because I need to make a carbon-carbon bond, and there are ways to make carbon-carbon bonds and alcohols at the same time. And the fact that we're not having the nucleophile come from this position is because this is a secondary carbon. We really want to reserve organometallics for doing substitution on primary carbons. We want to avoid substitution on secondary carbons.
I have a question on the radical halogenation. We did the bromine on carbon 2 because that's considered benzylic, right?
Yes.
Because it wouldn't form on the other side of the rings.
It's not going to form here, and this is because the mechanism has a radical intermediate, and that radical actually is conjugated to the ring, and it's delocalized, which means it's much easier to form because it's resonance stabilized.
Gotcha.
It could have formed here, though. Would that have been a problem?
No, it's the same.
Yeah, an achiral molecule, so it would flip over. What about this? Is this chiral or achiral? This compound. It's chiral. That's a chiral center, which means that step forms enantiomers, R and S, in a racemic mixture, so it doesn't really matter. Again, OChem 3 is where you'll talk about enantioselective reagents, so that you can just get one enantiomer throughout the whole structure. Yeah, some people call it OChem 3, but we don't.
Sorry, I have a question. Do you specify how many steps in your synthesis on the exam?
Not necessarily. Part of that is because students get confused. Does this count as 1 step or does it count as 2? I say it counts as 1. Because you can't do the Grignard acyl addition without the aqueous workup. But I'm not asking you to show me them separately either. So you have to show them separately, but they should be done over 1 arrow. The other reason that I don't specify is because there's often multiple right ways to do it. So I might have found a route and you took a longer, different route, but it still works, so I'm not going to penalize you for that.
It's like the Grignard, this, the one you showed us here.
Acyl
Not
addition.
an aldehyde.
That's a ketone, yeah. Ketones with acyl addition give us tertiary alcohols.
Doesn't have to be an aldehyde.
No, it can be formaldehyde, aldehyde, or ketone. This is a secondary alcohol. Secondary alcohols are only formed by acyl addition to aldehydes. Tertiary alcohols are formed by acyl addition to ketones.
This is the example of secondary alcohol?
Yeah, that's why we used an aldehyde here.
Could you have used a
I can't use a ketone unless I want to make a tertiary alcohol, and I'm not making a tertiary alcohol. Regiochemistry is what that all comes down to. I need a secondary alcohol, so I need a primary carbonyl precursor so that I can make another bond, another carbon-carbon bond. I turn a primary carbon into a secondary carbon by the acyl addition. All right, Roha, your question was on question 2, option 2, right? And I think that this goes to Cooper's question on organometallics forming rings. Yay, 2 birds, 1 stone. All right, let's map carbons and let's brainstorm as well. How would you guys map your carbons here? Any preference? Multiple right ways to do it? All up to what you prefer? Count from the alkene back through the ring? And where do you want to stop?
Before the bromine?
Also, can you remind me your name?
Brian.
Brian, thank you. Been a while. Good to have you back.
Yeah.
Stop at the...
Before the bromine at the end?
Okay, so like at the bromine carbon. There's 5 carbons. And where are those 5 carbons going to show up in the product? Well, actually the easiest to look at is carbon 5, 4, 3, 2, 1. All right, so I need to do some chemistry with carbon 5 to attack carbon 1. So there is some carbon-carbon bond formation. What's a good way to do carbon-carbon bond formation? One more time. Grignards. I'm making another secondary alcohol. What's a good way to make a secondary alcohol that involves Grignards? Have an aldehyde precursor. I didn't know my markers were in this kind of condition. I am so sorry. You could do this with no bromine. It would require a bromination step at the start. Well, this is an orthopara director, so one of the isomers you get. I guess there's another way you could do this, but not with the chemistry we have so far. You could do acylation, but in order to make the acid chloride, we're going to learn those reagents later on in the semester. Anything else that you guys think is going to be necessary? That's it? Where's my aldehyde? How can I make an aldehyde? First of all, what aldehyde or what carbon will be my aldehyde? Yeah, carbon 1 needs to become my aldehyde. Can we just show that precursor? Remember that we say we want to try working forward and backwards, so I can kind of redraw this. Here's 1, 2, 3, 4, 5. 5 needs to be an organometallic. That could be MgBr as well, totally legal. I'll show it as lithium here. 1 needs to be an aldehyde. In fact, this is not something you can isolate. So this is actually not a structure that I would even need you to show me. Because as soon as this forms, carbon 5 attacks carbon 1. Which means this needs to be followed with some aqueous workup because it will attack without anything else necessary. And as soon as it's attacked, I just need to protonate the alkoxide. I'm actually going to show how we can redraw it as 1, 2 later on because most of the time your aqueous workups are some second step. So now one of the questions is, did I make the aldehyde just before this happened, or did I make the lithium? Did I make the organolithium just before this happens? That's where we'll have to work forward and figure it out. Given that the aldehyde needs to be on carbon 1, any recommendations of how I can make the aldehyde? Or how I can get ready to pose that aldehyde?
I mean, this might add an extra step. You do hydroboration oxidation, and then turn that alcohol into an aldehyde somehow.
So, Abram, tell me, why do you want to do hydroboration oxidation of all the hydration mechanisms, of all the hydration reactions? Why this one? Good. Anti-Markovnikov gives the regiochemistry we're looking for. I want chemistry to happen on carbon 1, and I want that chemistry to involve an oxygen. So I need to put an oxygen onto carbon 1. I could have also done anti-Markovnikov HX addition, HX with H2O2, but that doesn't put an oxygen there for me to have an aldehyde. And what's a good precursor to an aldehyde? An alcohol. So if I need to make this aldehyde at some point, it just makes sense that I want to put an alcohol there to make the aldehyde. There are other ways to make aldehydes. If you guys remember, OCHEM 1, we learned that you can do carbon-carbon cleavage, alkene cleavage, to make aldehydes. Do I want to cleave any carbons? No. So I'm not interested in doing any cleavage reaction. So this works great. So again, remember, we were wondering, do I make the lithium to come to this, or should I do the lithium next and then do the oxidation to the aldehyde? Can I make my organometallic with this reagent as it is? The alcohol is the problem. If I make an organometallic here, the alcohol just protonates the organometallic, and I don't have an organometallic anymore. I have to oxidize first. What can I use to oxidize this, this alcohol into an aldehyde? PCC. Is there anything else that would work? No. There is nothing else that would work. Why not? Chromic acid gives me a carboxylic acid, and carboxylic acid is going to acyl addition. And it's not benzylic, so I can't do MnO2. MnO2 is too selective. So PCC is my only reagent here. The Des-Martin reagent would also work, but if you put the Des-Martin reagent on your test, I'll just be confused and realize that you studied not using our class materials. I wouldn't take any points off, I would just be confused. All right, now earlier I said that this reagent never actually forms. So I would never actually expect you to show me this reagent. Here's what I would expect you to show me. From here, we're just going to put first 2 equivalences of lithium. Wait, earlier we just did 1 equivalence of magnesium. Why is it 2 equivalences of lithium? Different groups on the periodic table. I need a 2 electron reduction, 2 equivalences of group 1 lithium, or 1 equivalence of group 2 magnesium. 2 equivalences of lithium makes this, and an aqueous workup of H3O plus makes this. You will never isolate this in the lab. There is something fun you can do with our NMR that we just got in the lab. You could actually mix these reagents together and stick it in the NMR while they're reacting, and you could take several scans of the NMR spectrum and you could watch as this transforms into this different chemical here. The hydrogen signals are going to change on the aromatic ring. And then watch as it forms into the alkoxide, where the aldehyde signal disappears and a new signal here appears. So all I would expect is 1, 2. You wouldn't even have to show me this intermediate. Here's what I was talking about earlier. I said I made a synthesis and I took it off of the practice midterm. It was a ring closing like this. And I just feel like those are confusing to see because I don't need you to show me this. And I knew a lot of you would do that, and that you were going to be counting your steps, and that you were going to be confused about why you had more steps than what I was expecting. So this is how you create a ring. In class, Cooper, we actually saw how organometallics can substitute other leading groups just by SN2, and that can form a ring as well. But here, we're not doing SN2. Instead, we're creating a ring by acyl addition. Ring-forming reactions with organometallics, carbon-carbon bond forming to create a ring, are always intramolecular reactions. One part of the molecule reacts with a different part of the molecule, closing those two parts of the molecule together, creating a ring. So if you ever find a problem like this, where you have a linear structure and then a cyclic structure, you're creating a carbon-carbon bond, so you should do organometallics, more likely than not. And you're going to use them to attack each other. Roha, how do we do on this?
Could we, for 2 lithium, could we have used the Mg?
Yep. Just as effective. Perfect. The only thing it changes is this. Other questions? Abram?
Could you have done that Mg step before you did the hydroboration, oxidation?
No.
No.
Because if you made the organometallic and then formed the alcohol, this organometallic just steals the hydrogen. This is the product you get if you did first form the Grignard and then form the alcohol.
It would have just left.
Yeah, well, remember, carbon holds these electrons.
Yeah.
This is basically like this. So it's not that it leaves. It becomes protonated. The functionality leaves. The whole usefulness of it, gone. You'd have to start over, and you'd have to brominate the ring again, and then reform the organometallic. So you cannot have the organometallic until you are ready to use the organometallic. Good question. Maddie?
My question was going to be, when you're in a reaction like this, will there be any time that an MgBr versus an Li would be better? So or are they just interchangeable completely?
Interchangeable completely for the purposes of our class.
Okay.
You get into a synthesis lab, you're going to find that some have one usefulness that, in a different application than another. But on paper, for our class, equal. Good question.
Any relevant other first reactions you could have done to make that alkene
Into the aldehyde?
Yes.
Longer reactions. For instance, you could have done HX anti-Markovnikov and then done SN2, substituted the halogen with water to make the alcohol, just adding on more steps. If you know that you need to have an aldehyde and you know it needs to be on that anti-Markovnikov position, you are going to want an alcohol as a precursor to the aldehyde. So it just makes sense to do an alcohol reaction, hydration reaction. Yep, oxymercuration wouldn't have put the alcohol in the right carbon though. I don't know if you guys caught this, but you have no reason not to turn in Unit 3 written work. You also have the a little bit more background to now try and do the other problems, but no reason you can't turn in your homework. Okay. All right. We had some questions from the practice midterm, so I want to take us there. These review classes go so fast, and I didn't even get a chance to say this, but I'm not going to take a break, but if you need to move or go to the bathroom, you're more than welcome to, but we just have such limited time. I feel like I can't take a break. Question 16. So, alcohol acidity, which is one of the topics that we wanted to talk about. We have 4 different types of alcohols. We have a primary alcohol, a secondary alcohol, an ortho alcohol to an electron withdrawing group, orthophenol, and a metaphenol. You know what? I'm actually realizing now that I don't think I covered everything on my acidity of alcohols in lecture that would have helped you answer this question. The acidity of alcohols is affected by induction. And I'll just give this to you now. The inductive effect isn't one that you would need to even answer a question like this on your midterm exam. But I'll quickly explain it. Inductive effect means that electron withdrawing groups pull electron density away from the alcohol, making it more acidic, or electron donating groups like alkyls push electron density towards the alcohol, making it less acidic, more basic. A primary carbon has less of that alkyl group pushing its electron density towards it, so this is less basic, more acidic. And this secondary alcohol has more electron density being pushed towards it, which makes it more basic, less acidic. So ranking the non-phenols, and we know that non-phenols are less acidic, more basic than phenols, because phenols have resonance in the conjugate base. That stabilizes the base, makes it a better acid. So C is actually, D is the most basic, the least acidic, because it has the most alkyl group pushing electron density towards it, making it a better base, a worse acid than C. But we did talk about the phenols, and that's something that you may need to use on your midterms. So talk to me. How can I compare the acidity of an orthophenol to an electron withdrawing group versus a metaphenol to an electron withdrawing group? We did a problem like this in lecture. Do both phenols have resonance in the aromatic ring? Yes. Do either phenol in the conjugate base have resonance that goes into the nitro group? Maddie, I saw you nodding your head. Do you want to tell me which one?
Oh, I may be wrong, but I think it's A.
A, the ortho position. Should we prove it? Because I think this kind of goes to Abram's complex problem. It's not exactly the same, but let's look at the conjugate base. Oops, I can't draw this because I need to do resonance. Let's look at the conjugate base when A gets deprotonated. And let's look at the conjugate base when B gets deprotonated. And let's see, I have abbreviated the structure because the other ring doesn't do anything. Let's see if we can get electrons up into the nitro group so that the nitro group can pull it. So here's the answer to your question, by the way, which is if the ring has a negative charge, electron withdrawing groups can pull that charge up into it. What type of reaction has a negative charge in the sigma complex? EAS or NAS? One more time. NAS. The nucleophile attacks the ring, pushes its electron density into the ring. Electron withdrawing groups can pull that up. Electron donating groups push electrons, a lone pair, does that look like a lone pair? Into the positive charge. What type of reaction, EAS or NAS, has a positive charge? EAS. The ring gives electrons to an electrophile, which creates a positive charge, and electron donating groups can push a lone pair into that positive charge. So this is neither EAS nor NAS, but it's going to feel a little bit similar. Let's see if I can take B and get my electrons over to the nitro group. Electron donating group pushes in. This pi bond here has to break. It can only break this direction. This carbon needs to lose the electrons. This carbon also owns the electrons. So if this carbon needs to lose them, this carbon gets to use them. Now this carbon needs to lose electrons, so I'll give them here. Okay, I'm trying to get electrons up into that group, but at the moment, this carbon is receiving electrons, and it needs to get rid of electrons, which means the only other thing I can do is push the electrons here. I was not effective in getting that negative charge into the nitro group. So meta electron withdrawing groups do not stabilize the conjugate base of an alcohol. And that was Maddie's prediction. Maddie's prediction was that the ortho group is stabilized. Oxygen shares its bond. This bond needs to break. It's owned by this carbon now. That carbon can share it with the nitro group. Orthopara alcohols, orthopara phenols are more acidic than metaphenols relative to these electron withdrawing groups.
If the two negative oxygens are just like slightly electromagnetic oxygens being next to each other will also contribute to that acidity, just due to proximity.
You've got inductive effect, true, but not as big of an impact as resonance effect. Resonance always has a bigger impact than induction. We can come back to this idea of will charges go in or out, because I know some people wanted to look at mechanisms. So, did this answer your question?
I'm still kind of confused about it, but
Then let's look at it in the context of these mechanisms, yeah? Any other questions on this? Acidity of alcohols before we move on? Oh, we had this other question though, which was the reactivity of the halogens. So this is asking us to rank these compounds by EAS, which is when the ring acts as not an electrophile. EAS, the ring is substituted by an electrophile. The ring acts as a nucleophile. So the ring needs moral support when it comes to electron density. The ring needs electrons. Who's going to give electrons to the ring? Good. So which of these compounds has the strongest and or the most electron donating groups? D has 2 electron donating groups, 2 alcohols. By the way, is oxygen the strongest donating group? What's the strongest? Not carbon. No, carbon doesn't even have electrons to give, typically. Sulfur is a withdrawing group. The nitrogen. Nitrogen is the best donating group. because it has a lone pair and it's not as electronegative, so it's more willing to share its electrons. But D has 2 donating groups. What would be next?
H2 or NO2?
NO2 is electron withdrawing. NO2 doesn't have any lone pairs on the end. What's the next strongest donator? C, which has an alcohol again. How does that compare to B? B is weaker. It still has a donating group, but it's not an alcohol. It's just a methyl. That methyl group doesn't actually have lone pairs to contribute, so it can't increase resonance. All C can do is place a positive charge on a tertiary carbon. Tertiary carbon holds a positive charge better. That's a more stable resonance form. Why is A the least reactive? It's got 2 deactivators. Bromine is a deactivator, and the nitrile is a withdrawing group deactivator. So A, 2 deactivators. B and C, 1 activator, 1 deactivator, different strengths of activators, same strength of deactivator. A, 2 activators. That one was nice to grade because it was A, B, C, D. Both of them were A, B, C, D. You know, I made a mistake and I've changed this in your exam. I didn't have the 2 options labeled differently, so people didn't tell me which one they were doing. And that wasn't a problem with 16 because they were both A, B, C, D. But I have changed that so that you guys have to circle which one you want to do this time. Okay, I don't think we're going to have time for this, so I think you guys are good on substitution and elimination. It's not going to be a very prevalent part of this exam. So the only things left for us to talk about are the mechanisms list, the examples of mechanisms, oxidizers, and roadmaps. Why did I want to talk about oxidizers again? Oh, you brought up the Des Martin. I think that was it.
Yeah.
The only oxidizers you will see: chromic acid, which is your strong one, PCC, which is mild, and MnO2, which is selective and mild. MnO2 does not make carboxylic acids, but it will only react on radical resonance stabilized positions. MnO2 has a radical intermediate. I don't know that we'll get to a chance for the roadmap. Roadmap is like plugging in problems, but we'll see what we can do. Okay. All right, so let's look at acylation mechanism. And let's have an amine group here. Actually, let's do something like this. Let's have both an amine and an alcohol. And let's add this isobutyl chloride, 2-methyl propanoyl chloride. Which of these groups is going to direct acylation? NH2 is the stronger director. OH is also a good director, but NH2 is a better activator because it shares its electrons more and stabilizes the resonance more because it holds a positive charge more easily. So NH2 is actually my primary director, which means that I have 2 products that I can get. One is when the acyl group is ortho to the amine, and one is when the acyl group is para to the amine. What's the first step of my mechanism? Activation. I'm actually going to hold off on drawing the aromatic ring right now because it's not going to play a role, and that can take a lot of time to draw that structure. In acylation and in alkylation, chlorine forms a bond with the catalyst. This gives me an activated complex. Aluminum has a negative charge. Chlorine has a positive charge. That's not done. The chlorine pops off. And as some of you saw in your unit test part B, there is a resonance form here. You can draw one or both. You could even show the lone pair from oxygen coming down now to stabilize that new product that forms. Now in step 2, our aromatic ring attacks from a position that is either ortho or para to the strongest activator. I think I'm more tempted to draw the para. It doesn't matter though, we're just drawing one. Is that okay with you guys? That means I have to use these electrons. So these electrons attack the carbon and break the pi bond back to the oxygen. What did I miss? Positive charge here. And now I get into my resonance forms. How many resonance forms will I have in this structure? 2? No, minimum of 3. Always a minimum of 3. But the whole point of these activators is that they direct orthopara because they can provide a 4th resonance form. So, first, I'll show my positive charge moving. Let me show my pi bonds moving. My pi bonds will move so that the positive charge is next to the nitrogen. Then I can show my nitrogen forming a double bond and taking on the positive charge. And then I can show the formation of my last structure, which is where nitrogen takes the electrons back, and then I move another pi bond in the ring. What's the last step of my mechanism? What do I need to use for elimination? Yeah, and my base is actually this Cl bonded to the AlCl3 minus group. So Cl takes electrons from aluminum, bonds to hydrogen. Hydrogen gives electrons back to the ring. This is how I form my final product. Abram, let me check back in with you. Do you see how the donating group was able to push electrons in to the positive charge? Electron donating group pushes a lone pair into the positive charge. That happened here. EAS, you should always have electrons coming in to satisfy a positive charge. It's with NAS where you see electrons coming out.
And it's the ortho-para ones that have 4. And
Correct.
Meta have 3.
Yeah, notice how the alcohol, which is meta to my product, or sorry, to my new group, the alcohol had no effect on resonance because it's meta. Meta positions never have an effect on the resonance, only ortho and para positions.
Do all electrons
So one more time.
For all 3 AS, is that only electron donating groups?
No, EAS can be run by electron donating and electron withdrawing.
So you mentioned the hierarchy between NH2 and OH, and I know that like kind of speaks to this. Do you have like a chart of which are the best, which are the worst?
We did it in class.
Okay.
We made a column, electron donating, electron withdrawing, halogens.
Got it.
And we ranked electron donating groups by their strength. We did not rank electron withdrawing groups or halogens. So the focus there on activating effects was just on activating effect of activators. But we're not looking at the activating or deactivating effect of the electron withdrawing groups. Abram, you got a follow-up?
And then NAS reactions?
Yep.
It doesn't have three.
No, NAS also has a minimum of 3.
Yeah.
But if you have an electron withdrawing group that is ortho or para to the halogen leaving group, remember that NAS requires a halogen. Then you get a 4th resonance form. That's why electron withdrawing groups promote NAS. Let's look at what happens when we have this cyano ortho to this bromine, and we run it with hydroxide to get para-cyano-phenol. I know you guys said you wanted to see an alkylation mechanism as well. Yeah, the alkylation is so similar to the acylation. There's just the chance of a carbocation rearrangement. What's the first step here? There is no electrophile to activate, which means you just do nucleophilic attack or addition. Remember, I'm always going to attack the aryl halide carbon. That's the leaving group. So I'm going to break that bond, and it doesn't matter how you draw your pi bonds. It just matters that you break your pi bonds in the correct way. This carbon needs to lose electrons, so this carbon gets to keep them. I get a negative charge in my structure. Notice how an electron donating group is not going to do any good for this reaction. What do I want? A group that can push more electrons in to a ring that has a negative charge? What I want is an electron withdrawing group that can help hold on to that negative charge. Once again, we will always have a minimum of 3 resonance forms, but with an ortho-para electron withdrawing group, I'll get a 4th. Always 3, minimum. If you haven't drawn 3 resonance forms, you've missed something. Let's push this negative charge closer to the electron withdrawing group. And now, let's expand the electron withdrawing group so that we can show the electron withdrawing group taking the electrons. I don't know about you guys, but I really love parallel double bonds. So that structure looks really nice. No, -1. This is neutral. Now the nitrogen pushes electrons back into the system. Because that's done, I can abbreviate it again. What's the last step? Elimination. And not deprotonation like we saw last time. I don't need a base to do elimination. I just need to kick off my leaving group. I'll reform aromaticity. Should I kick off OH or BR? Oh, good one. BR gets kicked off. And I get to my final product. after you do NAS once, you can't do NAS again, no matter how many halogens you have. Because you're putting on an OH group or an NH2 group or something like that, and electron donating groups stop NAS reactivity. So you'd only be able to do this once. Withdrawing groups speed up. But withdrawing groups like nitro, carbonyls, acyl groups, sulfonyl groups, those groups are put on by EAS. So you can't add a withdrawing group by NAS. You actually only add donating groups by NAS. And doesn't that make sense? It's a nucleophile coming into the ring, and now it's still willing to share electrons. So, Abram, did that wrap it up?
Yeah.
How positive charge in the ring, those electron donating groups share electrons. Negative charge in the ring, those electron withdrawing groups pull electrons. You will never see an electron withdrawing group pull a positive charge. It can't. A positive charge doesn't have electrons to pull. You will never see an electron donating group pull negative charge. It doesn't have any room for negative charge. It has an octet. It can share that octet, but it can't take electrons. This also has an octet, but it has pi bonds to break. Man, we're a bit over. Any last questions that I can touch on? Nayir, I think you brought up the roadmap, right?
Yes, I'll make sure to do all the
What I think is, what I do on my roadmaps, and I'll just be clear about this, I try to aim for an equal number of reagents and structures. One of the nice things about roadmaps, here's a tip to you. You have clues at the end about what needs to happen earlier on. So if you feel stuck on a certain part of the roadmap, move on. You've got other reactions that are not impacted by it, and in fact, hints about what you can do earlier on. Another thing I try to do, I'm not perfect at this, is I try to have reagents that you need to guess show up in multiple choice problems. It doesn't always happen, but there's a good chance that if you need a reagent here, you'll see it somewhere else on the exam. So if you're feeling stuck, just go do another part of the exam. Try something else. Was there anything else specific you wanted to know about roadmaps? Okay. In my opinion, roadmaps are worth a lot of points. This page was worth 16 out of 70 points. That's more than 20% of the exam. A lot of exams that I know of have, instead of a reaction like this, or a setup like this, they'll have like 5 to 10 reactions where you need to draw the product. And then another page, 5 to 10 reactions where you need to fill in the reagent. So this is me just combining those things and making it super interesting for you.
Are we going to be in this room on Thursday?
We are. There's very little chance. In fact, I think confirmed that we will not be in the LAC for at least 2 weeks. So this week and next week. But we'll meet here for our midterm. I'll send out a reminder so that you guys and those that didn't show up today remember to come to this room. What time do we start? 5 o'clock. I'm actually going to give like a 10-minute window for people to show up a little bit late, ask some questions, and we'll start at 5:10, 5:15, 90 minutes. What can you bring with you? One sheet, front side, with handwritten notes. You don't need to bring anything with a periodic table. You don't need to bring anything for NMR or IR. If you look at the questions on this practice midterm, you'll see that there are questions on spectroscopy, multiple choice questions only, but there's almost always bonus problems that deal with spectroscopy. So lean into that if that's your strength, but use those tables to your advantage. You don't have to put any of that stuff on your sheet.
Is it going to be like OChem 1 where we can do test correction afterwards if we need to?
We'll see. Like if you guys give me a 90% average, I don't know. But if we fall in a normal average, you know one of the reasons I like to do the exam corrections, right? No, I don't call it corrections. I call it exam analysis. Because you're doing more than just correcting it, right? You're giving me feedback, reflection on what you got wrong and why. Why do I like to give those exam analysis assignments? It's because it forces you or incentivizes you to sit down with your exam and figure out where your pitfalls were so that you don't fall into them on the final. So it does bring up your midterm, although it's usually a better advantage for people who do worse on the exam, and it's less of an advantage for people who do well. But I also find that bonus problems are disadvantaged, are disproportionate. People that do well do the best on the bonus problems, and people that don't do well sometimes don't even do the bonus problems. Rarely get them right. So I've thought about taking bonus problems out, and I've thought about never doing the exam analysis, but I've decided to keep both of them in because I find that they kind of fix themselves. So we'll talk about that next week after exams are graded. Maddie?
If we do really well, if you'd like to do that, would you be open to having like per person basis?
I give your exams back.
Okay.
So you're always welcome to do your exam analysis even if I don't give you points for it. But we'll talk more about it next week when grades are in. Hoping grades are in next week. With everything that happened this week, I feel like I can't guarantee anything. Maybe Canvas will even erase itself. Could you imagine? That would not be fun. I don't think that's how it works. No. I think you'd get a fresh slate, which might not be nice. You lose all that buffer that you had from the first half of the semester. Or maybe I just give...
Amazon's fixed its problem, so hopefully this doesn't happen again.
Yeah, fingers crossed. All right, guys. Happy studying. I'll see you Thursday at 5 o'clock.